Unit 9 is broken into two halves. The first half that are going to be related, but the first half of it is devoted to parametric equations. Okay, so we're looking at that first. There is some pre-calc involved here, but how much we've seen and how much we remember is not a huge deal. Really, we're just going to do kind of an overview of this and then look at the calculus applications. So a parametric curve is defined by multiple variables in terms of a third. With two dimensions, we have an x and a y, and both of those are written as functions of time. And then in three dimensions, we would also add a z that is written as another function of time. Now, it doesn't necessarily have to be time. We just kind of say at time t equals whatever, but motion is a really common application of this, so time makes sense here. Okay, so instead of having one function that models either just the horizontal change over time and another that models vertical change over time, we can put those together parametrically and say x is a function of time, y is a function of time, and then we can graph those together in Cartesian form. Cartesian meaning our normal rectilinear XY plane, okay? Like the one we're familiar with. All right, so to start this, let's make a t-chart, just like we did way back in early algebra or pre-algebra, where we would say x is equal to, and then we'd kind of take our standard -2, -1, 0, 1, 2, and then you'd fill out what y is. We're going to do that, but our t values are going to be the control variable here. So -2, -1, 0, 1, 2. If we need to add some more, we can. And then this is x, this is y. So I'm plugging -2. I'm plugging the t values into both the x function and the y function, and I'm going to get an ordered pair out of that. I just have different functions to get the x coordinate and the y coordinate separately, and I'll put them together to graph them. Okay, so if I plug in -2 to t squared plus t, I get a +2. If I plug in -1, I get a 0. If I plug in 0, I get a 0. If I plug in 1, I get a 2. If I plug in 2, I get a 6. Okay, so there's some x coordinates. And then plugging these values into the y function, the 2t plus 1, if I plug in -2, I will get -3, and then -1, -1, 0, 1, 1, 3, and 2, 5. Okay, so these two columns make up my ordered pairs. Okay, let me try to draw that a little more straight. Okay, and so if I start plotting those, I'm going to start at 2, -3. Actually, let me put some. We're going to go to 6, just because I kind of have an idea what it's going to need to look like. And then okay, so I'm starting at 2, -3, and then 0, -1, and then 0, +1, and then 2, 3, which kind of looks like I have some symmetry happening here over the x-axis, and then 6, 5. I went up to 4. That's okay. We'll put it right there. All right, now this might not be enough to kind of get the whole picture, but we can plug some more points in. So let's say we plug in for symmetry. Let's see. Let's try to plug in the next. Let's try to plug in -3. Okay, I'm doing -3 because I see this pattern 2, 0, 0, 2, 6. So I'm going 1 the other direction. So if I plug in -3, I'm going to get a 6 and a -5, okay, which is kind of what I thought that I would get based on that symmetry, but the -3 comes before. So really, if I'm thinking about this in order, that would be up there. Oh, there's my arrow. Okay, also, if I try to make this into a curve, which it makes sense that it would be a smooth curve because neither of these have anything funky going on independently, it kind of looks like I have a sideways parabola happening. Let's see if we can figure out what this, maybe a vertex or something is over here. I know that I went from 0, -1 to 0, +1 when t changed from -1 to 0. So let's plug in -1/2. If I plug in -1/2, I'm going to get a -1/4 for my x and a 0 for my y, which is going to be like right there. And I picked that because I was going halfway because of the symmetry. So really, I've got a curve that does look like a parabola that does this. Now, I can write the equation for that, and I will write the equation for that in Cartesian form. However, in parametric form, the direction matters. And so as t increases from a smaller number to a bigger number, we do need to indicate that we are going a direction. So I'm going to put a few arrows on here just to indicate that we have started from down here and we are moving like this as t increases, because there is no t-axis to show me that, okay? All right, so this is what the graph of the xy function written in parametric form looks like, okay? Now, you're not going to be doing a bunch of graphing with parametric functions, but I just wanted us to kind of understand how we can take two different functions, one for x and one for y, and put them together to get one two-dimensional graph, okay? Even though technically there are three variables. That third one ends up just giving us direction. Okay, as far as writing the Cartesian form, we need to do some substitution. Now, when our functions are given as like polynomial or root functions, those kinds of things, we're going to use substitution. If you have trig, which we'll look at an example in a bit that has trig in it, but if we have trig, then we're going to use trig identities for substitution. But here, just because I've got two pretty basic polynomials, I'm going to use a straightforward substitution where I solve for t in one equation and then I replace it in the other. So this one obviously is going to be easier to solve for t. So t is equal to y minus 1 all over 2. And then I'm going to take that and plug it in to the x function to replace t, and now I will have a function that is written in terms of, or I should say relation, an equation that is written in terms of x and y. So I have x equals y minus 1 over 2 squared plus y minus 1 over 2, which is y squared, I'm expanding this, y squared minus 2y plus 1 over 4 plus, and then common denominator, I'm multiplying by 2 over 2 here, 2y minus 2 over 4, which gives me y squared, negative 2y plus 2y, those are going to cancel, 1 plus negative 2, so minus 1 all over 4. Okay, does this reasonably look like the graph of this equation? Hopefully your answer is yes, because that is a horizontally opening parabola, and we also know that we have a shift of negative 1/4, which we did do that over here, and it has a horizontal shrink because we're sideways. Okay, anyway, that substitution process can get us from the Cartesian form to the rectangular form, okay? Let's do one more. I'm actually going to skip these two this one. If you would like to see it, I can show you that later, or you can, give it a try if you want. But we already did one practice problem with those. I want to look at one that has trig, because that's going to mean a lot more, especially moving forward into the second half of the unit. So here I have x is equal to 3 sine t, y is equal to cosine t, and then I am limited between 0 and 2 pi on my parameter, okay? So to get rid of the t, I need a relationship between this and this. Hopefully you're thinking sine squared plus cosine squared equals 1, which it does, and hopefully that stood out to you when sine and cosine are involved. I don't quite have sine though, but I can get sine by dividing by 3. So x over 3 is equal to sine t, and then cosine is just y. Okay, so then doing that substitution, I'm going to have sine squared, which is x over 3 squared, plus cosine squared, which is y, just y squared, equals 1 because of the Pythagorean identity. Okay? All right, so that's it right there for rewriting. Now, if we want to think about what the graph of this looks like, we could go through this t-chart process we did up above, or we could think about this with what we know about conic sections. And we could say, hey, this is the graph of an ellipse that is centered at the origin, that stretches, not stretches, but horizontally we move, this is my a squared. So horizontally we're moving 3 to the left and the right of the center to get the vertices. 1, 2, 3, 1, 2, 3, roughly. And then vertically we are moving 1 to get the co-vertices. And then let's see if I can make this look like an ellipse. Hey, not bad. Okay. And there we have an ellipse. Everything we have done so far is not calculus. It is pre-calc, but we need to understand how parametric functions work for them to make sense with calculus applications. Okay. And so I'm going to stop this, and in the next video, I'll do the calculus part, which is derivatives.